Section: Introduction. In this section, we discuss contemporary large language models, LLMs, and their capabilities in natural language processing. We note that these models have shown advanced abilities in language completion and reasoning, raising questions about their true intelligence and language learning skills. Our focus is on whether LLMs can understand the structure of a new language when given a few examples. We examine tasks where a model either generates a new sample or identifies if a sample belongs to a specific language. Some studies suggest that LLMs have a broad understanding of language structure, as they can produce grammatically correct samples from languages they haven't been trained on. However, their performance tends to be weaker with low-resource languages compared to those with more data. Critics argue that LLMs lack a true understanding of language structure since they learn from data rather than having an innate grammar. We do not see learning from data as a limitation, but we are concerned that a model might only grasp structures similar to what it has encountered during training. To explore this, we aim to evaluate LLMs using a benchmark that includes entirely new languages, avoiding any overlap with training data. Ideally, we would test models on language reasoning problems that are completely separate from their training and validation datasets. However, since training datasets are often vast and closed, it is challenging to ensure that new problems do not share similarities with previously seen content. To address this, we propose a method where we first define a comprehensive space of languages at a certain difficulty level and then randomly sample languages from this space. This approach helps eliminate bias towards familiar languages. In our work, we focus on languages recognized by three-state deterministic finite automata, which represent a basic level of complexity, but this method can be adapted for other difficulty levels. Our experimental results indicate that current LLMs may not be as proficient in recognizing language patterns as we expected, often performing worse than simple language models on basic tasks. This suggests that while LLMs excel in specific tasks, they may not generalize well to entirely new language reasoning challenges. In summary, we contribute by introducing a benchmark for evaluating LLM language reasoning that is independent of natural language web data. We assess several popular LLMs against this benchmark and find that they underperform compared to simpler language models. We also analyze how different factors, like reinforcement learning from human feedback and prompting techniques, affect the reasoning abilities of these models. Section Summary. In this section, we explore the reasoning capabilities of contemporary LLMs in understanding new languages by evaluating their performance on a benchmark of wholly novel languages, free from dataset leakage. Our findings indicate that LLMs underperform compared to basic language models, suggesting they may not generalize well to entirely new language reasoning tasks despite their success in specific applications. Section: DFAs and regular languages. In this section, we examine deterministic finite automata, DFAs, and regular languages, focusing on Type 3 languages, which are the simplest in the Chomsky hierarchy. These languages can be recognized by DFAs, with examples including binary strings that have an even number of ones and base 10 numbers divisible by 7. We note that finite automaton languages are equivalent to regular languages, which can be described using regular expressions. A key measure of a regular language's complexity is the number of states in its corresponding DFA, indicating the memory available to the automaton during processing. DFAs with two states have a state set that directly corresponds to the output set of 0 and 1, meaning they lack hidden states. Therefore, we focus on three-state DFAs, as they represent the simplest non-trivial case. We introduce a sequence completion task where models must finish a sequence that belongs to a specific DFA's language. This task is relevant because most language data encountered in practice will resemble this format, consisting of several example sequences followed by a distinct prefix that needs completion through next token prediction. To create test cases, we first sample a DFA, then generate 30 example sequences of length 10 that the DFA accepts, and finally select a distinct prefix of length 5 that does not match any of the 30 examples but can be completed to form an accepted sequence by the DFA. The goal is to find a completion of this prefix, ranging from 1 to 5 characters, that the DFA will accept. We evaluate models by sampling a DFA, generating 30 random problem instances, and calculating a binary prediction score for each instance, which indicates whether the predicted completion forms a valid string in the language. We then average these scores across multiple sampled DFAs to obtain an overall accuracy score. Next, we address the transducer task, which provides a more direct evaluation of pattern recognition without relying on world models. In this task, each input sequence is paired with an output at each token, with the final output masked for prediction by a language model. We refer to this as a transducer task because the DFA acts as a machine that transforms input sequences into output sequences. For example, if the language requires an even number of A tokens and the input is ABCABCAABBCCAA, the model receives an annotated string and must predict the masked output. This task is clearer than the sequence completion task since the model has access to intermediate outputs, serving as a proxy for the DFA's internal state. We also establish baseline models with varying complexity for the sequence completion task. The random baseline generates a random string of 5 characters, which may seem trivial but helps measure bias in our sampling approach. The common suffix baseline seeks a completion that maximizes occurrences as a suffix, ignoring the distinct prefix. The n-gram baseline examines the last n1 characters of the distinct prefix to find matches in the example sequences, returning the most common completion. Lastly, the brute force baseline tests all possible DFAs with 3 states and 3 symbols, filtering for those that accept the example sequences and evaluating all potential 5-character completions. While we do not consider the brute force approach a practical comparison due to its complexity, we view it as an upper performance limit for this task. Section Summary. In this section, we explore Type 3 languages recognized by deterministic finite automata, DFAs, and introduce 2 tasks: a sequence completion task, where models predict valid completions for given prefixes in a DFA's language, and a transducer task, which involves predicting masked outputs based on annotated input sequences. We also establish baseline models for these tasks to evaluate performance against various strategies for generating completions. Section: Transducer task. In this section, we discuss the transducer task and our baseline strategies. For the null_t baseline, we compare 2 approaches: always predicting 0 or always predicting 1 for a given deterministic finite automaton, DFA. The n-gram_t baseline involves taking the last n-1 symbols from the transducer sequence. If that sequence is unique, we use the result from the n-1 gram_t baseline. If it appears multiple times, we select the token that follows most frequently. If there's no clear majority, we choose the last occurrence. For the brute force_t approach, we consider all possible DFAs with 3 states and 3 symbols, filtering those that match the transducer sequence, and then predict the next token based on a majority vote, defaulting to 1 if there's no majority. In our experiments, we evaluated several open-source models, including Llama and Mistral variants, as well as code models like StarCoder and Qwen. We also assessed proprietary models such as GPT 3.5 and Claude. For open-source models, we used a local LLM server and evaluated on 1,000 distinct DFAs, while for GPT 4o and Claude, we limited our evaluation to 30 DFAs due to computational constraints. Other proprietary models were evaluated on 100 DFAs, and we reported results with 95% bootstrap confidence intervals. We explored 4 prompting formats: Basic, which provides no context; More EXPL, which gives some grammar information; COT, which includes reasoning space; and Red-Green, which frames the task as a word problem using a house analogy for DFAs. We created versions of these prompts for each task, labeled with subscripts for sequence completion and transducer prompts. While no set of prompts can capture all model behaviors, we believe our prompts reflect common strategies. Our main results are summarized in a table. We focus on valid answers, counting only those that can be parsed. In the sequence completion task, we found that it can theoretically be solved with near-perfect accuracy, as shown by the brute force _s results, although this method is computationally intensive. We primarily relied on n-gram _s heuristics, which often outperformed LLMs. Interestingly, the effectiveness of chain-of-thought reasoning varied. Basic _s worked best for GPT-4o mini, while red-green _s was optimal for GPT-4o. Claude 3.5 struggled with basic _s and more EXPL _s but excelled with COT _s. Additionally, code-specific open-source models generally outperformed sequence completion models, indicating a broader ability to generate strings from new languages. Overall, while LLMs showed some alignment with heuristic expectations, they still lagged behind simple n-gram heuristics. We also noted that uniform tokenization negatively impacted accuracy, as detailed in the appendix. Section Summary. In this section, we outline various baselines for the transducer task, including null _t, n-gram _t, and brute force _t, which utilize different strategies for predicting the next token based on given DFAs. We also describe our evaluation of multiple open-source and proprietary models using different prompting formats, revealing that while LLMs generally underperform compared to simple heuristics, the effectiveness of prompts varies across models. Section: Transducer. In this section, we examine the transducer task, which is generally less defined than sequence completion. We note that the brute force model achieves only 96.4% accuracy, but we believe that the relative results remain valid since all models face the same impossible problems. Our findings indicate that all large language models, LLMs, perform worse than a 4-gram model, suggesting they struggle with this task. Interestingly, the performance of the models does not align with their size. For instance, the open-source models Llama 3 and Mistral Nemo 8b outperform Claude and GPT-4o. We also observe inconsistencies within model classes, such as GPT-4o being outperformed by GPT-3.5, and Llama 3 to 70b showing similar results to Llama 3 to 8b. Additionally, Mistral Nemo 12b models perform comparably to Nemo Minitron 8b. We find that coding models do not show any particular advantage either. The lower performance of chat-oriented models suggests that this task is better suited for non-chat models. To ensure this is not just an issue with the basic prompt, we test several chat models with different prompts. Our results, shown in a table, reveal that even with chain-of-thought and word problem prompts, which aim to utilize the full reasoning capabilities of chat models, the performance remains poor, often matching or falling below that of the basic prompt on the transducer task. Overall, we conclude that LLMs struggle to perform the DFA transducer inference task effectively. This limitation does not stem from a lack of world modeling ability, as n-gram models do not create world models either. Instead, it appears that LLMs fail to recognize patterns when they come from unfamiliar sources, even if they are relatively simple. In our case study on the SUM Model 03 DFA, we illustrate this DFA as an arithmetic check where A represents 0, B represents 1, and C represents 2. The DFA accepts strings where the sum equals 0 Model 03. We focus on the transducer setting because SUM Model 03 is nearly impossible for both LLMs and n-gram models in the sequence completion context. We analyze two model prompt combinations, QB, which is the best overall performer, and CR, which is the best at providing explanations for our qualitative analysis. We present the number of errors each model makes on 1,000 instances of the transducer task for this DFA. We find that nearly all errors made by the 6-gram model were also made by at least one LLM, while the LLMs often made unique errors. Surprisingly, despite this task being better known than most DFAs, all three models perform worse on it than their average across random DFAs. We also conduct a qualitative analysis of CR's outputs on the red-green prompt to understand its reasoning. We sample 30 examples where it answered correctly and 30 where it answered incorrectly while the 6-gram model was correct. Our analysis shows that CR generally follows a 3-gram approach, learning rules about how previous outputs and symbols predict the next output. It learns that A does not change the output, while B and C transition a state from 1 to 0. These findings align with our earlier results, where we noted that 3-gram was the largest n-gram that any LLM outperformed. Although the model occasionally attempts more complex reasoning, it rarely succeeds. It also tries to identify periodic patterns but tends to recognize period 2 patterns more than period 3 patterns, despite knowing there are 3 states. Throughout our analysis of 60 reasoning traces, the model does not recognize that this is a version of the sum modulo 3 DFA or fully determine it in any other way, although it shows some signs of world modeling. For instance, it occasionally identifies 2 red rooms, but this does not lead to further insights. Overall, correct solutions do not stem from superior reasoning. Rather, they are more likely to be those that a 3-gram model would infer correctly, occurring in 5 out of 9 cases. Despite the theoretical computational power of transformers, without the ability to match patterns to existing problems, Claude employs a simplistic and ineffective approach.